Right, good afternoon everyone. Welcome to the next lecture in 49815. I've now moved out to the suburbs, living in Wakanda for the rest of June. I'm in a slightly more cramped recording space. I've got a lovely big room. You can probably hear the acoustics and maybe slightly more echoey than they were before, but my desk is quite a bit smaller. I have a standing desk, which is quite nice, but just this layout is not ideal. I can't get good lighting, which is why my hair is disappearing behind my green screen, and probably because I'm getting old as well. But that stuff out of the way, let's go through what we're going to speak about today. So I've put a lot of stuff up on the Slack site, and I've started hosting some codes on GitHub that I would like you guys to look at, develop and work out how they're doing as we're going along. So why are we looking at an aerodynamic databank, and what do we mean by an aerodynamic databank? We developed two sets of equations that we're going to use for modelling propellers and for our purposes. We developed the blade element equations. Let me just get the right pen up here. There we go. So the blade element equations, these enable us to determine for a given propeller, we can split the blade up into a set of two-dimensional sections. And the principle behind the blade element method is that these 2D sections are operating as if they would be in a two-dimensional flow field. So we can have an aerofoil section. We've got different, oh, this is not right, let me just lean my iPad better on here. We've got an in-plane velocity, which is Vt for our tangential velocity, and we've got our normal velocity. These two combine to give us a resultant. Let's call that Vr, which approaches the propeller disc plane at the advance angle phi. So this is our disc plane. We'll put our blade zero lift line on here. So we've then got this angle of attack alpha, and we know from two-dimensional aerodynamics that we're going to have some sort of lift, and we're going to have a drag as well. So we know all of these angles in here. So we can determine ultimately the whole propeller performance as long as we can work out what this lift and what these drag are. And in the methodology that we went through a non-dimensional set of equations where we assumed that we would be able to understand and determine what the lift coefficient, I should write that, two-dimensional lift coefficient, and the two-dimensional drag coefficient are. So what are these numbers? Now we have sort of an idea about what the lift coefficient is from two-dimensional aerodynamics. If we were to look at lift coefficient versus angle of attack, then we'd see some linear increase and we'd see some stall occurring at some angle. We've got a few things on here we can annotate. This gives us our CL max and our corresponding stall angle. And we sort of know that the slope of this is going to be around about 2 pi. So then if we were to look at these, dCl on d alpha is defined as A, which is the lift curve slope, and that's going to be 2 pi. For a purely two-dimensional flow, that's going to be 2 pi, and we get that from thin airfoil theory. So that's going to be the slope of it, but these curves can be displaced upwards, or they could be displaced downwards. Now that's determined by the camber of the aerofoil. Some aerofoils will also stall earlier, so we could have a stall here, or we could have an aerofoil that goes up and stalls at a much higher angle. So we need to have this behaviour. We need to know what is CL as a function of alpha. Now we sort of know what the slope is and what it's going to be, but we want to know exactly for a given angle of attack what is my lift coefficient. These are also further going to be a function of Mach number for a given aerofoils. So you'll see a different variation of CL versus alpha depending on the velocity with respect to the speed of sound. So we need to know CL and what CD are versus alpha for the sections of a propeller. So we're going to determine where we can get them from. So what we're going to initially look at are NACA 16 sections. The NACA 16 sections historically have been very commonly used on propeller geometries. They were developed back in 1940 by John Stack and a few other researchers, looking at aerofoils that could delay the onset of compressibility losses which were encountered on propellers due to the fact that they're spinning around and the aircraft's going forwards. So there's some papers that I've referenced you guys to look at in the papers repository. Now let's just bring those up now. So this paper is John Stack, I think I called him Slack, actually it's Stack. So this paper here is the genesis of these aerofoil sections. So tests of airfoils designed to delay the compressibility burble. It was John Stack, it was just on his own apparently. So I've given you guys this, or I've asked you guys to look through this paper, and I want you guys to determine I want you guys to understand them really. So I had an existing databank of NACA 16 data. Now I've never been able to find out where these data came from. The data were given to me during my PhD years and years and years ago, back when dinosaurs ruled the earth. So let's have a look at how I've converted those. So what do I mean by a data bank? Let's just make this small again. So these NACA 16 sections, I haven't really got a plan for today, which is why I'm a little bit all over the place at the moment. I've also written a Python notebook that helps us understand the NACA 16 sections a little bit better. That's available on GitHub, and it's in the same area as all these other parts that we've been going through. So this I wrote today was an introduction to NACA 16 sections, and I mentioned how there's two papers that we really need to understand to determine the aerodynamic properties of them. The first one is where do these come from? It's by Stack back in 1940, and then there was a series of tests done by Lindsay et al. In 1948. So importantly, in 1948, Lindsay showed the analytical expressions for how we formulate the shape of these aerofoils. So the camber line distribution was given in the Stack paper, and then what Lindsay goes on to give is these two polynomial expressions that determine the upper and lower surfaces. Now what I do here is we then plot one of these aerofoils based upon just two parameters. They are based on two things: the design lift coefficient and the thickness to chord ratio. So go through here and understand where things come from. I want you guys to play around. We can say we can look at this, we can change. Let's have a look at one that's 20% thick. Run it, we get a thicker aerofoil out. Let's have a look at one that's 5% thick. We get one that's less thick coming out. Let's say have a nice thick 20% thick aerofoil, and I'm going to set my design lift coefficient to 0.5. It's got less camber. So I want you guys to understand the relationship between these two parameters, CLD, which is the design lift coefficient, and the thickness to chord ratio, and what these look like when they come out. So let's put a really big design lift coefficient, 1.6. You probably never have one with anywhere near that camber. But here we go. We can look at them, and we can look at these profiles and see what they look like. So we can now look at what these sections look like. Now, I had a pre-existing set of data that was given to me back during my PhD, and I wrote a MATLAB script to interpolate between those data. So let's have a think about what I mean by that. So if we had a set of aerofoil sections, so we know a couple of things. We know that the shape of these aerofoils is given by two things. It's a function of something called the design lift coefficient and the thickness to chord ratio. So there's only two parameters that govern the shape of these aerofoils. So for a set of different aerofoils, if we had a variety of different shapes, a variety of different sets of these values, we could then do tests, determine CL versus alpha, say at 1 Mach number. Let's call this M is 0.3. Do a second set, M equals 0.4, and so on, all the way up to supersonic Mach numbers, say 1.4. We could then, this would all be then tied to a single set of, say, CLD 1, thickness to chord 1. We then change the aerofoil, do it again, and do it again. So we've then actually got CL and CD is a function of the design lift coefficient, thickness to chord ratio, alpha, and the Mach number. So there's a variety of different means that we can then take all of these data, and what we really want is the CL, the lift coefficient, and the CD. So I wrote a script to do this back when I was about 22 during my PhD. It wasn't very good, but this is the script that we've got. I sent you guys the MATLAB script over the weekend. This takes those data, so let's have a look. It imports a file called n16table.dat. So let's have a look at what that looks like. Let's load that up. It's a big set of data. Now what we have here are so we've got a bunch of tables. We've got table 1, table 2, and we've got, I think this is 10 columns wide and 20 columns deep here. So then we go down and we see actually we've got a lot of these. I know we've got 312 of these because I spent the weekend trying to decipher it again. So we've got 12 of these sets of data in here. Now it's not clear from this table and these data as they were given to me what they confer to, but they were also given to me with some accompanying Fortran code that made it sort of clearer that actually these upper first 10 rows and the first 9 columns are CL4. Now what we've got here in the columns, we've got different numbers of thickness to chord ratios, and then down in the rows we've got different design lift coefficients, or they might be the other way around, I'm not certain. But basically everything in this block is 1 Mach number and 1 angle of attack. And then down here we've got the same Mach number, same angle of attack, we get the drag coefficient. And what's the variation in the two spatial ordinates in this table is design lift coefficient and thickness to chord ratio. So I've changed my interpolation subroutine and I've rewritten it as a Python module. So this Python module, NACA16databank.py, imports the table, and then I'm pretty happy with how this works. So it goes through each of the 312 tables, and for a given design lift coefficient and thickness to chord ratio, it then determines what that table would look like, or where in that table the values you care about exist. It then creates 312 values and it then puts them into a new table, which is then the variation with Mach number and alpha for CL and CD. Splits them down into 2 subsonic and 2 supersonic tables, and then you can either spit those out and you can use them for your code, or you can just return the lift and drag coefficient. This is slightly less efficient using this method, but what this is useful for and what I've gone through, I wanted to check whether these data worked, how they actually helped us. And if we go back to the lift and drag coefficients, what I've done here is I've gone to this original Stack paper. So remember, Stack was 1940, tests of airfoils designed to delay the compressibility burble. So we can look at some of the data in here. We can see here, figure 4. There's some data. Let's move this over. So we can see here we've got some different aerofoils, we've got angle of attack, and we've got lift coefficient. So this first one here, it's a 16 section, which is what we want. Its design lift coefficient is 0, and it's 9% thick. Now the one below is design lift coefficient 0.1, 9% thick, 0.2, 0.5, 0.7, and 1.0. These are all design lift coefficients and they're all 9% thick. So then the discrimination between these lines isn't great. These were all hand drawn, but we can see here that obviously the design lift coefficient for this one has to be the CL equals 0 because it crosses the 0, 0 at that point. So we've got these 6 sets of data going up here. Now, what I've done is I've taken these data out, I've put them into this plot here, and I've compared what my interpolation of the Databank does compared to those experimental data. And then I've done that for two separate sets of aerofoils here. So there's 2 things that you guys need to be able to do to understand how to do this. The first is a really useful piece of software that I found, again, back during my PhD. I've never found anything as useful as this afterwards. This is called ENGR Digitizer. So if you have an old graph that you can't get the source data from, you can pick points off. So let's just clear this image. Let's start again. I'm not going to save those. We'll start a new one. I'm going to import a screenshot that I took, which was from testing these data today. So this is now just, it's got my graph in here. The very first thing I do is set the coordinates and set the axes for this graph. So I'm going to pick the lower left hand side. The x ordinate is -8 and the y ordinate is -0.25. Is that right? Yeah, that's right. Then I'm going to pick another one. Let's pick over in the bottom right hand side. The x ordinate is, well, let's be very careful here because there's 2 graphs being shown. We want the angle of attack, so it's going to be -8, -4, 0, 4, +8, that's going to be +12 there. So it'll be +12, and the x will again be -0.25. And let's just choose up here, let's say this line here, this was 0 and 1.2. So I can now move my cursor around, and I'm not sure if you guys can see that. Let me just change the scale of this image on here so you can see properly. There we go. So down in the lower, now down in the lower right-hand side of the screen, you should be able to see the coordinates change as I move around here. So if I move up to where 0, 0 should be on the graph, we get something very close to 0, 0 in those ordinates down there now. So what we can do with the graph, we can then just pick points off. So we can click here, and I'm selecting points for curve 1. And I want to then pick points from this first curve and get them out. I'm being kind of haphazard in the way that I'm doing this because I've already done all of these data before. So we're then going to, I just locked my computer, that doesn't help. What we can then do is we can then export those data. So those data come out, and it exports them as a CSV. I took all of those data out for all of those 6 curves, and I've just chosen to look at 2 of them. So because I was being a little bit lazy today and I didn't want to program this, I didn't want to code this all up, I just copied these data out and put them into my NACA 16 sections Python notebook. I've gone through, I've imported those, I've then plotted them as points on this graph. I've then imported the Databank, which is the bit that I wrote earlier. So this is this module, which I wrote yesterday evening. This does the interpolation for us. What I then do is I say, okay, I want to get those 4 interpolation functions. This is subsonic CL and CD interpolation functions, and then supersonic CL and CD functions. I supply to this the CLD and the TC, so that was 0 and 9% thick into here, and I then make a linearly spaced vector from the lowest to the highest experimental value, and I then work out what does my interpolation function think the lift coefficient is for those 2, and then put them onto the plot and I compare them, and actually they compare pretty damn well for these 2 that I've just checked. So what I want you guys to do is figure out how this bit of code works. So you don't necessarily have to go through every step of what this interpolation function is doing, but I want you to have an appreciation for how to use this piece of code. I want you to then go to this bit of code here. This is the NACA 16 sections. You should pick some aerofoils out of the stack paper. So choose some other aerofoils and then compare performance. So what have we got here? That's drag coefficient. I'd like to see the drag coefficient compared as well. What we've got here, this is again just an increase in Mach number. So this would be a change to the Mach number. That would be changing on these. That would be changing 0.3 to 0.45 here. We're then going to, let's see what else have we got in this stack paper. Fundamentally, I would like everyone in this group to pick out a different figure and try and repeat or compare what the Databank says is going on with what the data from this original stack paper are. Now, I'm not certain where those data came from for my Databank. I know the company that gave it to me, but I don't know where they did the tests. I think the tests might have been done at my old wind tunnel, but I don't know, there's no test report with them. So what I'd like to see is just how well do those data compare, how well do they perform. If you can pick some of those aerofoils out of that stack paper, this stack paper, and then compare them in there, I'd like to see how they compare. We've also got this second set of experimental data. This is from the Lindsay paper. What have we got here? These are actually, from first glance, these are not particularly nice graphs to look at. It looks like these are actually slightly poorer quality, but it might be worth a bit of a comparison in here. So I'd like you guys to take a bit of initiative in working out what's going on with these data here, work out how this Databank works, and then this will give us confidence in using CL and CD, because importantly what we've got now is over on, if I look over in my Spider command window, you can see what I've written here. So NACA 16 Databank, I can immediately see for a design lift coefficient of 0.1, for a thickness chord ratio of 9%, travelling at Mach 0.3 and alpha of 4, these are what my lift and what my drag are, according to the Databank. So we could use that in our experimental code when we look at the performance of propellers. It's going to be really useful. So there's a lot of stuff that I've given you guys today, lots of papers to look at. This IPython or the Jupyter Notebook, and then also the this module here. I'd like you to look at it, be able to use it, check that you can supply arguments to it, check that it works. Now, when we import this here, if I just close down the console, if you're working in the correct area and we then say import, you guys can read that, import NACA 16 Databank. If we want to say make interpolants, if we want to understand or we've forgotten what the syntax looks like, we can do NACA 16 Databank.make interpolants. And as soon as I press the open bracket, it will tell me here. It gives 4 interpolant objects for the design conditions given. Subsonic and supersonic, CL and CD interpolants, which are a function of alpha and Mach number. And it asks you for 2 arguments, one of which is the design lift coefficient, one of which is the thickness to chord ratio. And if you don't supply either of those, they both, well, if you don't supply one of them, they default to 0.2. So take those codes, have a look at them. We're going to have a discussion on Wednesday during our group session about how people have got on with this. I'm going to record another lecture tomorrow on how we write some of our performance codes, but this bit today is quite open-ended. I want you guys to take the code that I've written, modify it, play around with it, check that you can get it to work. And fundamentally what I would like to see is, can you compare how our aerofoils work, or sorry, not how our airfoils work. I want you to say, okay, well, I've picked out an aerofoil from the stack paper. CLD is equal to 0.55, TC is equal to 15%. Take those data out and I say, okay, well I've got some experimental data that I've picked out for CL versus alpha. I've picked those out using ENGR Digitizer, and I've then got my data. This is what the Databank says. So Databank, and this is from Stack. And what I'd also like to see is do the same thing for CD versus alpha. So this would give us an indication of whether we can use this Databank for our experimental results. I know that the previous implementation of this in MATLAB works well, but I've never properly validated this Databank. So I'd like you guys to help me out with that. So it was a quick video today, but I did a lot of writing to get the codes to a stage that you guys can handle them. So use the papers that I provided in the papers repository, go through those codes and compare some of those aerofoils. And if you're having problems, put it on the Slack space and we'll talk about it as the week goes on. Okay, I think this is probably about two or 3 hours worth of work to just get your head around how these work. If there's problems with Python, if there's problems with any of the things I provided, put a message on Slack and I'll respond pretty fast on that. Okay, I look forward to speaking to you guys on Wednesday. I'll set a time up for that and we'll arrange when it's going to be. And there should be another quick video lecture on some of the codes that we need to create tomorrow.